I will begin with some scripture here. I believe this is John 16:33. There it is. These things I have spoken to you, so that in me you may have peace. In the world you will have tribulation, but take courage. I have overcome the world. So this is John 16:33. Begin with a word of prayer. Dear Heavenly Father, we thank you for this time we have just to meet together and study linear algebra. Just pray that you'd guide our steps today, help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So I think we're safe today. I think the CFA has left us. If any of them are... See, it would be very embarrassing if they actually watched online and saw my inevitable besmirching of them in their absence. But, oh well. They're probably busy being in school and stuff, so... Let's see here. So today we're talking about linear transformations. So in some sense, linear algebra begins today because linear algebra is the study of linear transformations. But, I don't know. So like what gets called linear algebra, you know, I would say properly speaking, it's kind of half linear algebra really and half matrix theory. We've been predominantly focused on matrix theory up to this point. And we still will be for the rest of the course. But linear transformation, the concept of linear transformation is central to like the true study of linear algebra. So here's the definition for us. If t is a function from Rm to Rn is a function. So that notation means function, but I'm just going to write it again to emphasize, is a function, and number one, t of x plus y is t of x plus t of y for all x and y in, oh man, just a second here. Other way around, I want my bad, and the n comes first in my usual nomenclature. The m comes second. So n as in nenu nenu, m as in mommy. So t of x plus y is equal to t of x plus t of y. This property we can refer to as additivity. And number two, t of cx is equal to ct of x. Now some people will call this homogeneity. My brother objects to that because he says homogeneity is something else. But Bill's not here, so he can't stop us. If you want to, you can call it homogeneity. Really what it's saying is that the scalar multiplication factors out. I mean, have a little bit less clumsy way of... Anyway, so I don't really want to give this a name. But if you take both of these together, I refer to them collectively as linearity. Linearity of t. Now, so for us a linear transformation will be one on column vectors, right? But let me just take a step back here and let's take a walk down memory lane for a minute here. And what are some other examples of linearity? Can you think of some other examples of linearity? If we drop the so dropping the Rn domain, okay? Can you guys tell me some other examples of linearity before we go on and do easy stuff with matrices? Nobody? Your favorite thing? Limit. Right? The limit is linear. Right? It breaks up across sums, and you can pull constants out, right? And then what did that imply the linearity of in turn? How about the derivative? Right? The derivative of sum is the sum of the derivatives. You can pull a constant out. What else? Oh, integration, right? Integration has linearity. Yeah. With the proper understanding. If we're talking about indefinite integration. Anything else? Have you guys had differential equations, anybody? So what else, what other linear operators did you learn about in there? This thing? Yeah, the Laplace transform is linear. That's right. The improper integral is linear. Right? In calculus 3, this thing is linear. This thing is linear. In calculus 1, this thing is linear. This one is also linear. We could be here all day. Like, there are many, many examples where what you're dealing with is a linear transformation. However, the difference between all of this and what I have up here is significant. What's the difference? Here we're talking about, usually it takes what's the input. Typically what these are doing, what? There's some kind of box. You've got your operator. What goes in? A function, right? What comes out? New function, right? So both the domain and the codomain, if you will, of all of these, for the most part, ignoring like the definite integral, it just takes in a function, outputs a function, right? This is an operator, a linear operator. A linear transformation, on the in contrast, that terminology is talking about what it sounds like you're transforming column vectors from one thing to another. And a little bit more language here. If T is a linear transformation from Rn to Rn, then T is a linear, well, let me say if this, my bad, and T is linear transformation, then T is a linear transformation on Rn. So we actually spend quite a bit of time in here studying linear transformations on Rn, like on R2, on R3, stuff like that. Let's look at some examples. So example 1, we could have T of x. This is going to be kind of like an uber example, but suppose T of x is equal to AX. For like x, a column vector in Rn, and A is a constant matrix. What do you want to make it? What size would that be? For this multiplication makes sense, it'd be what? Rm by n, right? So is this a linear transformation? Let's work it out. So we have T of x plus y is equal to, sorry, I meant to throw this over here. Whoa. Whoa. Nice. That was all right. All right, so now you guys are awake. That's good. X plus y. And then by properties of matrix multiplication, we have AX plus AY, right? Which is what, by definition? T of x plus T of y. Yay. We have additivity. How about homogeneity? Or pull the scalar out property. I'm going to call it homogeneity. Sorry, Bill. He's not watching. Who do I care? So A times CX, like that. And then property matrix multiplication, pull the scalar multiplication out, which is what? All right. So I said this was an example, but the truth of the matter is this is really a theorem, right? What's our theorem? Theorem. If we have L sub A defined by L sub A of x is equal to AX for A in Rm by n and x in Rn, then LA is linear transformation. Oh, by the way, hey, that seems like a nice abbreviation, LT, linear transformation. Let's go with that. Unless you guys just want to keep spelling out linear transformation like another 1,000 times in this course. So we can call it LT. So that's a theorem, right? If that, then that. That's what this example proves, actually. Which is super nice, because then anytime we want to prove linearity, what do we need to do? If we got a formula, if we can rewrite the formula as matrix multiplication, guess what? We're done. So let's look at example 2 here. Let me remove this unpleasantness from the board. There we go. Example 2. Suppose you've got t of x, y, z equal to, I don't know, x plus 2y, y minus 3z, x plus y, and 3x plus y plus z. Does this define a linear transformation? And if so, from what space to what space? So what does it take for something to be a function? I said at the start of all this is a function. Some of you have had Dr. Sprano's calculus, I think. Maybe not, maybe so. What's the first thing Dr. Sprano says in Calculus 1 if you had him? What's a function? It is a what? It's single valued, right? Single valued function. So is this single valued? Yes. It's not especially interesting. Is it linear? I don't know. What do you think the function is here? So here we're looking at t from what? What's the input? The input is 1, 2, 3 dimensional. So notice that the input comes last. Excuse me, the input, my bad. Input comes first. What am I saying? Goodness gracious. All right. How many dimensions do we got? 1, 2, 3, 4. So we're going to R4. Okay. And let's see here. Let me suggest the following. We can rewrite that formula as x times 1, 0, 1, 3 plus y times, 2, 1, 1, 1 plus z times 0 minus 3, 0, 1. That's it. Or perhaps if I write it in the less sneaky notation, it's helpful. So we've got x plus y times this plus z times this. But you guys, what does this mean? What's the matrix that we can, there's a matrix multiplication we can write here, right? What do I put in the box? Nobody? Surely somebody can tell me what to put in the box. Yeah. 1, 2, 0. Okay, yeah. Let's go indeed. Okay, so 0, 0, 1 minus 3, 1, 1, 0. You guys are weird. 3. I mean, I would say the first column is this. The second column is that. The third column is that. But you guys are reading me the first row. That's fine. We do have a habit of reading rows sometimes. Anyway, there it is. So what does this mean? Therefore, t is equal to L sub A, where this is A, right? So A is a what? It is a 4 by 3 matrix, right? Consequently, this is a what? This is a linear transformation, okay? So if you can write the formula as a matrix multiplication, it is a linear transformation. So definition, if T from R n to Rm is a linear transformation, then the standard matrix of T is denoted bracket T like this, and is defined by bracket T is equal to T of E1, T of E2, dot, 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 T of En. Where those are the usual standard bases. So to find the standard matrix, you simply take the linear transformation and you plug in the standard basis, and the matrix that you get, that's the standard matrix for the linear transformation. Now, there's another little theorem we can prove here. Not a big one, but theorem. If, linear transformation T from Rn to Rm has standard matrix bracket T, then L bracket T is just equal to T. In other words, well, yeah, let me just leave it at that. That's the theorem. The theorem is that the formula for the matrix is given by multiplication of the standard matrix. Like this right here, in my example 2, A is literally the standard matrix of T, all right? In retrospect, that's what we found. That's the standard matrix of that linear transformation. Now, this is a theorem. I'm claiming that these two functions are the same. How do you verify a claim about functions being equal, guys? Do you know? What do we need to do? How do you know two functions are equal? What does it take?
The same input provides the same output.
The same input provides the same output. Yeah, for every possible input, right? So let's here's the proof, right? So let's look at. We could start on either side. I'll start with T. So let's look at T of x. All right. Well, that's T of the sum I equals 1 to n of x sub I e sub I, right? Because any vector in n dimensions can be written as a linear combination of the standard basis, right? Then we can do what? Well, then we can use the additivity and the homogeneity of this to pull out the summation and to pull out the numbers x of I, and that just leaves us with T of ei, like that. But what are we looking at? We're looking at exactly like x1 T of e1 plus x2 T of e2 plus plus xn T of en, which you guys should recognize as nothing more than the matrix like T of e1 glued together with T of e2 glued all the way with T of en, multiplying the column vector x1, x2, xn. So again, we're using that. Matrix multiplication can be recognized as a weighted linear combination of the columns of the matrix. But what is that? So this right here is the standard matrix, right? So what are we looking at? We're looking at the standard matrix T times X. That's X again, right? Which is by definition left multiplication by the matrix, standard matrix of T, acting on X. So I've defined a couple things today here, guys. Like the one is this L sub A map. L sub A means it's a linear transformation where you're left multiplying by the matrix A, all right? That's one definition I've made. So you need to know that in terms of notation. The other notation, which is far more standard, is the standard matrix, right? So this L sub A is not as standard a notation, but you will find it throughout my notes. So it's standard in that sense. But now this holds for every single possible input. Therefore, what do we get? Therefore, the linear transformation T is equal to left multiplication by its standard matrix. All right. Now, so I've been doing if then, right? Like if it's a linear transformation. Well, maybe we're done actually. Let's see here. So we have, if it's a linear transformation, right? Then that implies it's a matrix multiplication. It's just put this theorem in words. What it's saying is that if your function is a linear transformation, then its formula is exactly matrix multiplication, right? My example one was what? If your formula is matrix multiplication, then it's a linear transformation. So you put these two things together, what do you have? You have a biconditional, right? You have a function from Rn to Rm is a linear transformation if and only if its formula is exactly matrix multiplication, right? So if the formula is not matrix multiplication, it's not a linear transformation. Right. So like I guess I should give you at least one non-example, right? So here's one. Oh man. Yowzers. Example 3. How about this? F, a mapping from, let's say, R2 to R2, something like f of x comma y equals to x squared plus 4xy plus 3y squared. Why is this not a linear transformation on R2? Many reasons, right? One obvious reason, well, you're like, well, you can write that as a matrix multiplication, right? Because if you look at it like this, right? You could put a matrix here, write it as a matrix multiplication of sorts. Can you fill in the box to make that formula true? I'll do the easy part. 1, 3. There are actually infinitely many answers for the other two, but a nice choice would be 2 and 2. Okay, very good. I see some celebration. Nerds. Let's see here. So it takes one to know one. Fair enough. Yeah, so when I say the formula is a matrix multiplication, I really mean specifically it's left multiplication by a single matrix. That's the formula I'm talking about, right? There could be another way to use a matrix that wouldn't count as matrix multiplication. This would be that, okay? This example here is actually not a linear transformation. This is what's called a quadratic form. So this is an example of a quadratic form. Quadratic form on R2. If you want, you can like write the formula for this as something like this. Generally speaking, Q of V is V transpose, let's say BV. That would be the formula for a quadratic form. And for a quadratic form, if you put in a constant, well, you get back a constant times the vector transpose times the matrix times the constant times the vector, which you can pull a c squared out of. So this function, to be technical, this function is homogeneous degree 2. This is what people would mean by homogeneous degree 2. Linearity, we want homogeneous degree 1. We just want to be able to pull out a constant just like that. We shouldn't pull out the square of a constant like this, right? But that's what would happen for this, right? If you put in a 3x and a 3y, you get 9 times the output for this formula, right? Anyway, not a linear transformation. Are we good? All right. New transformations from old. What can we do? We can talk about T1 plus T2. We can talk about a constant times T1. And we can even talk about T composed with S. All right. So here I'll let T1 and T2 be linear transformations, say from Rn to Rm. And I'll let T be a mapping from, say, a linear transformation from Rn to Rp. And I'll let S be a linear transformation from, oh man, my bad. I meant to say S goes from there. I always mess that up. S goes from Rn to Rp. T goes from Rp to, let's say, Rm. I want them to be composable. So like T composed with S. Let me draw a picture. So like there's 3 spaces I'm thinking about here. So we've got Rn, you got your middle space, Rp, and you got your final space, Rm. The linear transformation S goes from there to there. The linear transformation T goes from here to here. So like going straight from here to here is T composed with S. The way composition works, the last shall be first and the first shall be last. Right? Like T here comes last in the way this works. All right, so you can define a sum or a scalar multiple or even a composition of linear transformations in these ways, right? So what do you think the definition is going to be? It's like back to pre-calculus, right? How do we find, you remember how we define the sum of functions? Pointwise, right? Still true here. So like T1 plus T2 is defined by T1 of x plus T2 of x. And CT1 is defined by CT1 of x, right? And composition means that you take one of the transformations and you plug it into the other. So this is T of S of x, like that. We can show that each one of these new transformations from old is in fact, again, a linear transformation. So like theorem. These are linear transformations. Right? Again, assuming that T1 and T2 are linear transformation, and T composed with S is a linear transformation. What do you think the standard matrix of T1 plus T2 is? What if you do like, you know, so what would be the standard matrix of T1 plus T2? I'll work that one out. It's rather silly. This would be, so what? We do T1 plus T2 of E1, T1 plus T2 of En. So how's that go? We've got T1 of E1 plus T2 of E2, T1 of En plus T2 of En. But you can break that up into T1 of E1, T1 of En, plus big matrix here, T1, T2 rather, of E1, T2 of En. And now for the conclusion of this exciting proof, T1 standard matrix plus T2 standard matrix. So yeah, shockingly, the standard matrix of the sum of two linear transformations is, guess what? The sum of the standard matrices of the transformations being composed. Yeah. This is not a hard thing to show. As you can see, I just did it right there without too much work. What about composition? How's that work? Let's work that out. What is the standard matrix of the composition of two linear transformations? How do we understand that? Let us work it out. If I can find my markers. So how do we find the formula of the standard matrix for a linear transformation? So we have T composed with S, right? We're trying to find its standard matrix. So what do? If we want to let's figure out the jth column of it. What would that be equal to? T composed with S acting on what? What is the jth column of the standard matrix? You take the standard, you take the transformation, right? And you feed it EJ, right? This is the definition of standard matrix, actually. So what is that? What is the definition of composite, though? This is what? This is T of S of EJ, right? By definition of composition of functions. Okay, but how does this work? Well, remember we have the theorem that says that's the standard matrix of T times this vector, right? But applying that same theorem again, remember the linear transformation S can be written as what? Matrix multiplication, the standard matrix of S times EJ, right? So this is the standard matrix of T times the standard matrix of S times EJ. And what is this? Well, this is nothing more than the jth column of the product of the matrices, standard matrix of T times standard matrix of S. So therefore, thus, we find the following result, that the standard matrix of the composite is simply the product of the standard matrices of the transformations being composed. By the way, if you're more curious, so sometimes you guys are more curious. If you were a more curious bunch, you might have been like, why have you defined matrix multiplication as you did, like a month ago? It's a really kind of weird definition, isn't it? In some sense, it's a very weird definition. If you just multiply matrices in MATLAB, it might do some weird thing, like it just multiplies each component, right? Component by component, and gives you a new matrix that is just multiplying component by component rather than this, which is a much more complicated thing, right? But the reason that we define matrix multiplication as we did is, of course, because it has given us all the wonderful theorems that we've seen about solving systems, right? But in addition, because it's natural with this concept of function composition. See, it's exactly this rule that matrix multiplication was designed to implement, right? Matrix multiplication really was invented so that this would happen. That's the truth. All right, so next up here, what do linear transformations do exactly, right? Like, how should we understand a linear transformation? It's easy enough to figure out whether or not a given formula is a linear transformation, right? But what does a linear transformation actually do to vectors in the plane or in space? Like, how do we understand the action of a linear transformation? Is there something we can say about it? So one of the first things I always work through is this. If we define a line, if L is a line with direction vector v and let's say base point p, let's say that that's a notation. So here I'm talking about p plus tv such that, you know, p and v are elements of, let's say, Rn, and t is a real number, right? So just to graph this schematically, this is the point set, which has like a base point of p and a direction vector of v, right? And the set of all points, this is a subset of Rn, right? The line with direction vector v and base point p, right? Line with direction v and base point p. Natural question to ask. If you have a linear transformation, what does it do to a line? Right? Can we figure this out? So if I have t, a linear transformation from, let's say, Rn to Rm, what happens if I look at t of L of v comma p? What do I mean by that? What is t of a set? Maybe you haven't thought about this before. What does it mean to take a set of values and feed it to a function? How should we understand that? See, what you should understand that as is a set of values. It's called the image of the line under the transformation. So specifically, what this means is simply this, t of x, such that x is an element of the line. That's all it means, right? But we can be more specific here because this line we have characterized with a base point p and a direction vector v. And so what we're really looking at here is t of, well, p plus tv, such that t is a real number, yeah? Does that make sense? Do you see what I did? What is x? If x is in that line, that means there exists some time such that p plus the time times the direction vector gives you the point on the line. That's an arbitrary thing. So it's the same set of points there. And now we can use linearity. See, we can use linearity. So this is t of p plus little t times t of v, such that t is in R, right? But what's that? Now you got to use your imagination a little bit. I've just introduced a new definition, right? Like, really, this is a definition for the sake of this lecture. I don't know. I don't think this notation is in my notes. It could be, though. I am a creature of habit. So if I made it up one day, I might have made it up another day, you know? But it's been a minute since I wrote these notes. I think these notes make reference to, like, Sonic on Ward's Road. It's been a minute since that was there. I remember eating cheeseburgers at Sonic with Dr. Sprano. It was nice. They were good. It was a good Sonic. Anyway, that is what? That is the line, right? With base point what? Well, what's the direction vector of this line? The direction vector is t of v, and the base point is t of p, right? But this line is a subset of what? It's a subset not of Rn, but of Rm. So what does this little calculation show us? It shows us something incredibly useful and really a guiding principle for graphing linear transformations is that linear transformations map lines to lines. That's what this proves, right? Our input was a line, our output is a line. Unless what? I mean, I say it's a line, but even up here, for this to be a line, what do I really need? There's a little fine print that needs to be attached to that, isn't there? We need this is not equal to 0, right? If the direction vector v is equal to 0, it's not really a line we're talking about. It's just a point in space, right? And similarly here, I really need that t of v is not equal to 0. See, because if t of v was equal to 0, it wouldn't be a line. It'd just be a point, right? You're like, you mean linear transformations can map lines to points or points to lines? I mean, well, we can't map a point to a line, but we can map a line to a point. Example, well, here, I'm going to put this down here. So probably one of the most important examples of linear transformations are the projections. And so like, what example am I on? 4? All right, so example 4, t of x comma y equal to x comma 0. So here, if we're talking about a line like this, which would be something like what? Maybe L of, P plus what? Plus TE2? Where's that map to? So think about it. If we've got this is specifically the set of points like P1 comma P2 plus T plus T. Well, under this projection map, it just maps to not that line. My bad. I don't mean to say that line. I mean to say just the single point. P1 comma 0, right? On the other hand, if you had a horizontal line, right, like this one, it would just map to itself under this T. Well, that's not true either. What happens to the horizontal line? It's kind of dumb. So this one would be what am I got? Oh, yeah, P1 plus T comma P2, right? What happens to that one?
I think I shifted to the 0.
Yeah, exactly. It gets projected down to here. Yeah. And if you had a, if you had a slanted line, it would just get, everything gets projected down to the x-axis by this projection. It's kind of boring in that sense. I have some more exciting pictures though in my notes, which I'd share with you here if I have time. Hey, I started class 2 minutes late, so I've got like at least 4 minutes left, right? All right, see if it's, come on, work. Let me find my laser. Come on. Ah, yay. So here, what I do in these notes, and this would take me forever and a day to work out on the board, so I'm very grateful for the projector here because we can get a lot with a very short time. So like here, the linear transformation is defined by x comma 2y. So what this is doing is it's rescaling the vertical and keeping the horizontal just the same. What I do in all these examples is I map the unit square to whatever it goes to under the linear transformation in question. And so I know that is logical because remember, lines map to lines, right? And that then means that intersections of lines map to their intersections as well. So long story short, you can map a linear transformation's action on a rectangle simply by mapping the corners. Because remember, to make a line, we just connect the dots. So all I really need to do to understand the total motion of the unit square is just to map its four corners. All right? And more on that as we go on because, well, yeah, but through that one. This one here, diagonal matrix, standard matrix, K and K on both. That just like basically blows the whole space up both directions by a scale factor of K. Here is, come on guys. This one is -1, -1. What that does is it flips things over the origin. It's an inversion, as they're known, like that. Here is 1, 2, 3, 4. 1, 2, 3, 4 takes the square and squishes it. I'll be done here in like 30 seconds, guys. The 1 over root 2, the rotation matrix rotates, shockingly. Let's see here, arbitrary angle 1, great. I wanted to get to and here's the projection. The projection will squish either that way or that way. Those are different projection maps. And let's see here, finally, I have over here a picture. Oh, come on, seriously? Ah. All right, I guess class is over. I was going to show you a unit cube for a 3-dimensional input, but oh well. I got some color coding if you look at that. If you're looking at the notes in